Thank you for being here. I'm very happy. My name is Ricard Delgado. I'm from CSEM, that some of you may know. I'm the head of the embedded software group, and today I'm going to talk to you about wearable AI. So I'm going to try to push a bit this concept of edge. Next, please. So for those who don't know, CSEM is actually a public-private partnership. So we are an RTO like Fraunhofer and companies like this. So we develop the technology and then we transfer it to the industry. So I just want to get this out of the way, so you won't find a CSEM product on the shelves. Usually we transfer technology, we create startups, we make the IP and so on. We are for non-profit, so anything that we do, we reinvest in let's say in new research. Can you just go for the next one? Yes. So in terms of wearable, we've been on the market for we've been an active player for a long time, usually in different form factors. So right now it's quite trendy, the fact of having like a wristbands or smart watches, but we have been as well like playing into shoes, or what we call right now is the smart headphones or hearables as well. The same thing for patches, either adhesive or something embedded in clothing. And as you can imagine, all these devices are pushing the definition to the edge to really something that you have to wear, and you have to be like really low power, right? Can you just go to the next one, please? So we can all agree that machine learning is really disrupting the classical machine learning algorithm, the classical algorithms that are embedded into small devices. So we used to develop quite a lot of and optimize signal processing based algorithms. So in fixed point implementations and SIMD instruction and so on and so forth. So machine learning and in particular neural networks, which are quite trendy right now, are also suited for this kind of optimization. And we agree that there actually are like three main drivers that are pushing us to start using these kind of algorithms inside the device itself, instead of in a backend or in the phone or in some kind of gateway. Right. One of them is data privacy, right? If you're monitoring some kind of vital sign, if it doesn't leave the device, then somebody cannot infer more information than necessary. There is a very important thing of latency. There was a discussion today about what is actually real time. For us, if you have to send something to a cloud and come back, you can make it very fast, but the latency becomes an issue, right? So I struggle to call this something like that in real time. So for us, the machine learning algorithm should be deployed into the device itself. And clearly the power consumption. So machine learning based algorithms are much heavier than traditional signal processing. However, sending raw physiological data through the Bluetooth or Wi-Fi and so on, it's also very heavy. Just go to the next one. So just to show you, we'd like to show you a small use case that we did in-house during this past year. We focus on one of our prototypes that you can see here on the right is a 2-lead ECG. So it registers, you have like a Swiss franc next to it, so you can imagine the size of the devices. It has like an onboard memory, Bluetooth, and so on and so forth. And we deployed one of our neural networks, the one you can see below, for detecting cardiac arrhythmias. So in how we proceed is like we took this model that it was trained on a large database on a cloud, and then the model was compressed, quantized, and implemented into a system on chip. In particular, we used the Nordic Semiconductor's NRF52, which it has a floating point unit, but our implementation that doesn't actually need that. So in terms of trade-off, as you can imagine, there is always, the more compressed your networks, the worse result you may get. But if you go to the next one, please. Okay, here is, I would say, maybe click once more so it appears. Okay, so here is the landscape of the different models which are competing to ours in terms of accuracy. Just check on the horizontal axis is in logarithmic, so you can see how quickly the number of parameters just skyrocket. However, as by the way that we have for compressing the networks, we can lose a bit of performance in terms of F1 score, but actually we can easily get one order of magnitude below in terms of matter, which makes it embeddable. Just to finish, on the right, you can see TensorFlow Lite is starting to implement similar tools to ours. We can decrease quite a lot in terms of energy and memory footprint. Next one. So this is my conclusion. Thank you very much. If you have any questions in terms of embedding machine learning, I'm happy to answer.